Okay, good afternoon and welcome to our presentation regarding our study, the design of lunar structures.
I'm Samantha Derrick.
I'm Kevin Jogger.
David Conley.
I'm Kunal Gangoli.
And I'm Amelia Miller.
In our presentation, we will cover the background information regarding our study, as well as the goals and purposes of our research. We'll also cover major topics regarding the construction and function of our lunar base, and we will end with a conclusion. Most of the challenges we faced were due to the lack of atmosphere on the moon. These problems include extreme temperatures, exposure to radiation, and micrometeorites. Other challenges we faced include light variation, gravity, food supply, and psychological needs of the crew.
So the main goal in our study was to design and develop a structure that can both withstand extreme conditions on the moon and also provide a permanent habitat for humans. This structure is known as Lunar Habitation 1, or LH1. And when it is up and built on the moon, we would like to study how living on the moon affects people and look into future colonization of the moon. And finally, we would like to look into utilizing the moon's natural resources.
The location we selected for our study is Malabar Mountain. It is situated on the south pole at the given coordinates. The reason why this location is ideal for our operations is because it has 74% daily illumination, and the greater amount of sunlight will allow for a greater amount of solar power available to the crew members. Malabar Mountain is also in direct line of sight with Earth, meaning that they can have direct communications without need of any type of relay station. Malabar Mountain is also geographically mature, meaning that the lunar soil, or also known as regolith, is a lot more thicker and it's easier to excavate. Malabar Mountain is in close proximity to lunar ice caps, which can provide the crew with water as well as fuel in the form of hydrogen and oxygen. And finally, Malabar Mountain experiences minimal radio interference because it blocks most radio signals coming from satellites orbiting Earth, and therefore it is an ideal location for a lunar radio observatory. The structure itself is going to be an inflatable structure. Inflatable structures essentially function like balloons. They're initially empty while they're being transported, and they're inflated once they reach the moon. The structure will be made out of 2 fibers of Kevlar 29. Kevlar 29 is a very strong industrial material, which is also very lightweight. The structure, there's going to be two fibers of Kevlar 29, and in the middle it will be filled with rigidizing foam, and that is what will give structural support to our building. The entire structure will be covered with regolith, and the regolith is very efficient at dealing with extreme temperature fluctuations, as well as keeping the radiation and micrometeorites out of the structure. The structure itself has a central hub. The central hub will have 3 floors, and it has 4 hemispherical domes radiating out of it, each with a different purpose. And finally, the dimension and square footage of the structure was determined using data gained from the International Space Station about how much area they give to each of their inhabitants.
So this is a blueprint of a cross-sectional view of the interior of LH1. As you can see in the center module, there's 2 floors which create 3 levels. The topmost floor lines with the floors in the external modules, and the dimensions are shown in meters. So in the in the central hub module, in the interior, there's again a support structure of 2 floors and 4 support beams. In this top view of the central module, you can see the layout of the 4 support beams around the center of the hub. The entire support structure is made of titanium, which is a metal that's very strong, but also relatively lightweight, which makes it a great aerospace building material. So the top floor, which is the ground floor, will be a living area, but also primarily a command center for LH1. So any infrastructure necessary for running day-to-day operations of the base will be present there. The level below that is the basement, and it's where the crew will be living. So beds, kitchen, a laboratory, residential facilities will be in the basement. And then the level below that is curved in conjunction with the natural shape of the inflatable, so it's unsuitable for habitation, but it will be used for storing unneeded equipment and supplies. So the external modules are connected to the central hub via corridors. These corridors are semi-elliptical, so this is a cross-sectional view of the corridors with the rigidizing foam layer in black and the floor in gray. The external modules themselves are hemispherical. One of them will be used for scientific research, and so it will house equipment necessary for astronomical observation as well as studies of the lunar environment. And the other 3 external modules will be used as greenhouses, so they'll be capable of providing artificial lighting to account for the lack of sunlight permeating the base, as well as climate control to create the necessary conditions for growth.
Now, following the development of our 3D model, we utilized ANSYS workbench in order to analyze the stress impact on the structure. The 2 stresses that we had studied are the internal pressurization, as well as the gravitational force of the regolith or lunar soil on the structure itself. Note that the underground portions of the structure will have little to no impact on the stress, as it has fixed support. Note for the upcoming graphics that red and orange represent maximum stress and deformation, while green and blue represent minimum stress and deformation.
So first, the central hub. As you can see, the most stress on the central hub on the exterior walls is at the top of the dome. On the inside of the structure, however, the most stress is present on a ring around the edge of the dome. This is due to the meeting of the two different geometries, the hub on the dome on the top and the elliptical walls around the edges. So the maximum amount of stress is there because there's added strain on the structure. However, the most amount of stress present on the structure is only about 31% of the yield strength of the foam. Any structure that has maximum stresses of anything less than between 50 and 60% of the yield strength of whatever material they are made out of are considered safe for habitation, meaning that the structure is very sound. So the deformation of the central hub, this shows as it reaches equilibrium. The deformation begins at the topmost point on the dome and spreads outward as the structure deforms slightly outward. So next, the hallways. The stress on the hallways, there's not a lot of stress. Again, only 22% of the maximum yield strength of the foam. The most stress is present on a ring around the bottom edge of the structure, where the bottom of the hallway that is attached to the lunar surface meets the top section that is freestanding, which again causes more strain on the structure. So for the deformation of the hallways, as they reach equilibrium, the external gravitational force of the regolith pushes down on the structure, making it bounce slightly inward as the middle of the walls bulge outward a little. Next, the external modules. The maximum stress is about 35% of the foam's yield strength, so again, structurally sound. It's a relatively constant stress around the entire dome, even more so on the inside walls of the structure, because it's a hemispherical shape and pressurization is constant across all of the structure. So for the deformation of the modules, as they reach equilibrium, the internal pressurization is a greater force than the gravitational force of the regolith, and so the whole structure deforms slightly outward, leaving it with the maximum deformation around the middle of the dome. But again, it's insignificant compared to the thickness of the walls.
So one of the big advantages of using an inflatable structure for a lunar base is that it can be packaged and transported to the moon at a very small percentage of its fully deployed volume. But the problem of how to do that efficiently and without harming the membrane is a complex one. So there are two simple methods of packaging that we looked at, coiling or wrapping and Z-folding. Coiling being flattening the uninflated structure and rolling it around some sort of central hub, and Z-folding being flattening the structure and folding it back and forth upon itself, much like the letter Z. For LH1, we elected to use coiling because Z-folding produces severe deformations in the membrane as you're forced to make definite creases to make those folds, which have been shown to hinder airflow upon the deployment of the base. So this chart on the right is a chart of dimensions of various coiled configurations based on the diameter of the central hub, which correlates to how tightly the membrane is rolled around the hub. As you can see, as the diameter increases, the volume increases, and the percentage of the fully deployed volume also increases. But the revolutions, which is the number of times the membrane has to be wrapped around the hub, decreases, which is good because a smaller number of revolutions reduces deformation of the structure. So we concluded that diameters between 1 and 1.5 meters were optimal as they struck a balance between reducing volume and reducing deformation. When we were determining whether a given volume was acceptable, we used the now defunct Space Shuttle's cargo bay as a benchmark, and we found that all of these dimensions fell well within those limits. In terms of the actual inflation gas necessary to blow up the structure to full size, we would need about 3,000 cubic meters to inflate the structure. NASA currently has designed tanks for the International Space Station that hold gas at 6,000 pounds per square inch. At this pressure, the necessary inflation gas would occupy less than 8 cubic meters, which again is very doable for a payload to space.
So the main reasons that we decided to add greenhouses into our structure were because of the food supply that it could provide for the inhabitants living there, the research opportunity to study how plants grow on the moon, as well as the improvement in air quality because of the carbon dioxide that the plants can take in and the oxygen that they put out. Growing plants has also been known to be very psychologically beneficial because it is a familiarity to life on Earth. So these are the 7 plants we chose to grow in our greenhouses, and that's all based on the health benefits that they provide, like vitamins, minerals, and macronutrients. In the greenhouses, we will be regulating the temperature, humidity, and light. And we'll be using artificial light because it is much easier to regulate, and getting natural light into our structure is extremely difficult. We will be growing these plants hydroponically, which means they'll be grown in water without soil. And this is found to be very successful both on Earth and in the ISS. And we are going to group these plants based on the climates they live in on Earth. and each different greenhouse will have a different climate. So we're going to group kale and spinach together, carrots, white potatoes, and finally sweet potatoes, black beans, and lentils.
In order to run the functions and processes of our lunar base, we elected to utilize two different sources of energy. The primary source of energy will be solar energy. Solar energy will be very useful on our location on Malapert Mountain, as we receive 74% illumination. Using solar panels, we hope to obtain solar energy. These solar panels will be located at the peak of Malapert Mountain and will be protected by 2 layers of fused silica glass in order to protect it from space debris. The secondary source of energy will be nuclear energy. In the cases that solar energy is unavailable during 26% of time that the lunar base experiences darkness. Nuclear energy is also a very pragmatic source of energy for a lunar base, as helium-3 is very abundant on the moon. Helium-3 is a helium isotope that is very useful in the production of nuclear energy.
So there are a few topics that we would like to do further research into or see further research into, including the effect of airlocks on the structural integrity of an inflatable base, more in-depth analysis of the design of the internal structure inside the central hub, as well as the potential for using a base like LH1 in the future as a site for either an astronomical observatory or a staging site for missions to Mars and beyond. But in terms of the conclusions that arose out of this research, we've demonstrated the feasibility of inflatables and rigidizing foam as a mode of lunar design in that they're volume efficient and they can support their own weight via the stress analyses. We've shown the practicality of a polar location like Malapert Mountain in terms of sunlight availability as well as communication with Earth. We've demonstrated the importance of research into space agriculture, as the greenhouses and the operations therein do constitute a significant part of what LH1 does. And overall, the attainability of lunar colonization. While it is several decades away at a minimum, there's significant conceptual, technical, and design work already being done on bases just like LH1.
And this study would not have been possible without many people and organizations, so we would just like to thank our mentors, Professor Benaroya and Nitika Yadapali, as well as Dr. Rosen, Dean Antoine, the Governor School of Engineering Technology and all of its staff, and Hackerspace. We would also like to thank all the sponsors, including Rutgers, the State University of New Jersey, and Rutgers School of Engineering for making this program possible. Thank you, and we're now going to open up the floor to questions.
What program did you use for the simulations that we saw?
The stress simulations were all done using ANSYS Workbench, and the actual structure was modeled in SolidWorks, which is the CAD software.
How would you get the bottom underground? Because I understand inflating, but wouldn't you need to dig space for the bottom to inflate to the ground? Or?
So one of the things about a project like this is, as I said, it's several decades in the future at a minimum. So when we designed it, we made some assumptions, the biggest of which is the advancement of technology you would expect to see over several decades. So we assumed we would have some robotic mechanism of excavating enough regolith to get the base underground. Yeah.
Would it reduce gravity a little bit, the fact that people living in structures?
So we actually accounted for that. It's 1/6 the gravity that we have on Earth. And what we did was we actually extended the dimensions and made it higher so that the people living there were comfortable and accommodated for when they were living in the structure.
In terms of like medical changes, probably. The truth is nobody's ever permanently resided on the moon for any significant period of time. So that would be something that we could do research on if a base like LH1 were constructed.
Do you have some idea of the total mass of all this, of the material that we're going to have to bring from Earth to the moon, and about how much energy that would take to transfer it?
We didn't, that went beyond the scope of our question. Yeah.
Can you explain the comment about helium-3 in relation to nuclear energy, and where is helium-3 on the moon? How do you extract it?
Sure. Well, helium-3 is found on the surface of the moon, I believe, and helium-3 aids in the process of the production of nuclear energy as it removes the risk of radiation. So there would be no health risks to the crew members.
Yeah.
How many people can be accommodated on this base?
So the base is designed to accommodate 10 crew members, and what Kevin said about the dimensions of the base being taken from the ISS, the per capita square footage of the ISS we used. The central hub has a square footage of about 4,000 square feet. on both levels, which is about 400 square feet for each of the 10 crew members, which is a pretty significant amount for a space structure.
Okay, that's it. Thank you very much.